Thank you, everyone, for joining in. My name is Suman Debnath. I work for Anyscale. I predominantly focus on distributed training and inference. So today, what we are going to talk about in next 10, 15 minutes is a bit about what is inference and how it is different from training. I have some resources which I can share after this session. But if you have any questions, feel free to ask, and I'll share my contact towards the end. You can always reach out to me. Okay. All right. With that in mind, uh, let's talk about a life of a token. So the way that you should think about token is, if you're not familiar with this, is in this inference world, is every time you ask a question to ChatGPT or any LLM, what you get are a sequence of tokens. You can think of it like a word, which is not technically correct, but for the sake of the discussion, you can consider every word or a subword is a token. So what happens is, uh, typically we are talking about a transformer architecture. There are different architectures to for generative models, but for the sake of the discussion, let's assume that we are dealing with transformers. So what happens is, you start with your input, you give the first token, and then it goes through the transformer block, which consists of multi-head attention, feed-forward network, and all that. And then we have multiple of this. This is just one transformer block, but we have multiple of these transformer blocks. And finally, we get a probability of the next token out of our vocabulary. So assume that our vocabulary is, let's say, 10,000 tokens. The output of that would be a matrix of 1 by 10,000, where it would be it would contain the probability for each of those tokens, and we will pick the maximum likelihood of of the token which we feel should be the next token. And then we feed that again to the transformer block, and it keeps on continuing. For example, here we have the same transformer block, but just for visual understanding, what I have done is I've kept it all together, one after another, and assume that we have the input sentence as "Welcome to OpenXdata. How are?" That's all. Okay, I'm just giving this much of data. So what is happening is, it is going through the transformer block all together in one go, and then at the end, what we want the LLM to generate is the next token or the next word, which might be feeling, right? So welcome to OpenX data, how are you feeling? Now, this is what is different in inference than training, because in inference, what we generally do is, we we pass the prompt or the question first, right? That's the question that you generally give to ChatGPT, that goes all together, and then we expect the next token, right? So we just expect the output of the last token. We don't care about the output of all this token at the inference time. During the training time, we do consider that, but for the inference time, all that matters is the last token output. Right? So in a nutshell, we give the whole thing together and we process it all together, and we do this just to get the first token. And when we do the initial pass of all this together, our passing our prompt, that is called prefill, right? So that means this is where we are doing a massive computation. So the bigger the prompt is, the larger the context is, we have to do more matrix multiplication. And that's why we call this as a matrix to matrix, or GEM, a general matrix multiplication operation, from a GPU standpoint. Whereas in the decode stage, we just take this last token, this is the first token, and then we keep on iterating over it and generate the next token one after another till we reach the limit, whatever we have set for the maximum output, right? So let's say we have set a limit of generate just 100 tokens, so it will just stop at the 100th token, or if it reaches the end of sequence. So whatever reaches first, we will just stop. But the point to note here is, in inference, we have two stages. One is prefill and another is decode. So the prefill stage is the first stage when it takes the input prompt and process it and then generate the first token, only the first token. So this is a compute bound operation because you have to do a lot of matrix multiplication. But after that, you just take that next token that is here in this example feeling, and then you feed it, and then you don't compute the whole attention what we have done in the pre-fill stage, because we all cache this for optimization. We will see how that caching works, but we just cache it. So after the pre-fill, in the decode stage, we just generate one token at a time in a sequential manner. And that's why it is more memory bound, because every time you generate a new token, you have to load from the cache of the previous computation and perform the forward pass. So fundamentally, prefill has a different requirement in terms of AI infrastructure, and decode has a different requirement in terms of in AI infrastructure. So that is what you need to be cognizant about. Now, if you think about inference engineering, it comprises of three layers at a nutshell. One is the runtime, which shows how fast one GPU can go. And here we are talking about a model which is deployed by you, not by, let's say, Anthropic or OpenAI, because they have done everything at their side. And how we are interacting with them is just through an API, right? So they have done all this inference engineering at their side. But now, if you have to do it with an open source fine-tuned model or any open source model, how you would plan it, right? How you would deploy it? That's the biggest question. You cannot just download a model from Hugging Face and deploy it and load it in your laptop or in one server. It cannot work. It cannot scale when thousands of people will be interacting, just like how ChatGPT works, right? We all interact at the same time, but it still works. So runtime defines how fast your GPU can go. Infrastructure layer is when it comes to scaling, right? How you can deploy that model such that it can serve millions of users. And tooling layer is kind of a gluing layer which can take care of both of this together, like infrastructure and as well as runtime. And the example for tooling layers are, you can use tools like or frameworks like vLLM, Ray, SGLang, and so on and so forth. Whereas in the infrastructure, you can make use of all these different parallelism technique, where you can split the model into multiple tensors or multiple blocks and make all the GPU work together. So for the next 5 minutes, today we cannot go over all of this, but we will look into KV cache and speculative decoding, because these two are important constructs when it comes to inference engineering. So KV cache is very simple and very intuitive. Uh, let's say you start with these prompt once upon, right? This is just the input token that you have. So you have to compute the key value metrics, and you have to compute and you have to do the forward pass and then generate the next token, which is A. Now, the first one is the prefill stage. Remember what we mentioned? Prefill just takes care of the first token. And once we have the first token, after that, everything is decode. Now, if you see, after every token we generate, we are doing a same computation over and over and again, right? Like for in this case, in the first prefill case, we did the computation to see the attention of upon with respect to its previous tokens. We have done this in the decode stage 1, decode stage 2, 3, and 4, in all of them. So if we don't use any KV cache, then we have to do it over and again for every decode. Whereas with KV cache, we will just cache it. So every time we perform, we do a token generation, we just cache the key and value for the new token. And that's how you can implement a very efficient inference system. So this is a very complicated diagram, but I'll share you a link from where I've taken this. There's a beautiful book called Inference Engineering Illustrated. I just found it a couple of weeks back. And when you look at it, when you read through that book, you would understand how KV cache actually reduces the computation. You don't have to do that many number of matrix multiplication because you are caching it. And to give you an intuition, if you see where my mouse pointer is, you see here the query, key, and value. So every time you generate, you have to have the same size of all of this. Whereas if you use KV cache, you just compute the query, key, and value vector. That is the just one dimensional vector, and then you just load every time you just load from the cache, and that is what uh, it is showing in the yellow color here. So again, this is just at very high level, but I'll share you the resource. But the point to take here is with KV cache, you can reduce the computational cost and make your inference system faster. And to implement that, you can just use any of the framework, vLLM or SD-Lang or even transformers as well. And if you see here, you just use a flag called use cache. In this case, we are using transformers, but if you use vLLM or SD-Lang, there is a different flag. But it's very straightforward. There's nothing difficult there. Now, the last thing that I want to talk about today is speculative decoding. So, what is that? And just to remind you, all of this, whatever we are talking about, like KV cache, speculative decoding, quantization, these all are at runtime. Right? So, just to go back and have the mental model right, we are talking about all this runtime layer optimization. So, the objective of this is how we can make the inference system work very fast in one GPU. Once we know how to do that, then we can scale it across multiple GPUs using tensor parallelism, pipeline parallelism, and so on. Right. So that's when the infrastructure layer comes in, right? Because inference engineering is very convoluted and very vast. So a lot of times we have seen that developers get a little confused, myself included, when we talk about all these different techniques, then toolings, and etc. So just to set the context that we are talking about only runtime today. We've talked about KV cache. And the last thing that we will talk about is speculative decoding. So what is speculative decoding? Imagine that you have one model, very big model, right? Let's say billion and trillion parameter model. And if you have to generate a token, we will just generate like how we generate generally. We give one token at a time. Let's say the red blocks are the prompt, the initial prompt, and then it just generates one token at a time, and we feed that token back, and then we generate the next token and keeps on going. Now, this is fine, but it takes a lot of time because it's a very big model. It takes a lot of time to load. It is again the KV cache because bigger model will have a bigger KV cache. So what we found that with speculative decoding, what we do is we take a small model called a draft model, and this draft model is very very small with respect to the main model. And what we do is we use that small model to generate a lot of token at the same time. Again, the small model will also generate token one at a time, but it is small, so the latency for that is very very low. Now what we do is we just generate a lot of token at the same time. So in this case, if you see here, we are generating all these token from the small model. Now we are not yet done. This is just the first phase. After that, what we do is we take the bigger model and then we send the whole prompt together along with whatever the small model have generated. And then we try to compare what the smaller model has generated and what is the probability that the larger model has for that particular token. and then it just does because this happens in one pass. Okay, so this just happened in one single pass. It just sends the whole prompt together, and now we just see the probability of each of those tokens which were generated by the draft model. And let's say the draft model has generated these four tokens, 1, 2, 3, and 4. What we will do is we will see that what is the probability of these tokens by the target model at the end. So this is what the target model has predicted, let's say, and we will just compare the probability of these tokens with respect to these tokens, and we can have a threshold, let's say uh, a threshold of, let's say, 70%. That means if the target model is which is the bigger model, is 70% above for the token that the draft model has generated, then it will just send it to the user. But the moment that target model feels that okay, this token is not good, this token has a very low probability, that means anything that it has generated after that is not valid, right? So it will just stop till here. So it will just stop giving the user only these two tokens. So in the best case, if the draft model is generating k number of tokens, then you can generate k tokens in one go, right? So that's the efficiency gain that you are getting with speculative decoding with a small model. And the worst case is the target model has discarded, all the tokens starting from the first token that the draft model have generated. So in that case, you will not get any benefit, right? So that's about speculative decoding. And again, in the code, if you would like to implement, uh, again, for vLLM or SGLang, it is just one flag. But if you want to do it through transformers, since you need two models, you define the target and the assistant. Assistant is nothing but the draft model, and when you generate, you just give the smaller model and the target model. That's all, right? So there is nothing fancy that we do.
Nice.
So that's about speculative decoding, right? So
Suman, I think we're just about to. I think we're way over time, but if you have
yeah,
just another few seconds, if you
yeah,
want to
yeah,
wrap
yeah.
up, yeah.
Yeah, I'm almost done. So this is the last slide. So the takeaway is prefill is compute bound, decode is memory bound, and KV cache is something that you can use to leverage inference. And always remember that one GPU can work in testing, but not in production. So in that case, you have to rely on a distributed and infrastructure, and that's where SGLang, Ray, and all these frameworks comes in. All right. So with
Nice.
that, I'll just
Suman, I have a feeling, and this is also both listening and reading the chat, that everyone would love to have a Suman in their pocket because you make it seem like the whole thing is so easy.
yeah, yeah.
I it's kind of amazing. Here we go. Daniel says it almost seems too easy when he explains it. And Abhijit says this is hands down the most ground to earth explanation I have seen for AI token systems. So well done on your pedagogic skills, Suman.
Oh no, thank you so much. Yeah, I think we had a very short time, but I just want to share a couple of resources. The link which I've shared, I would highly recommend that images I have taken from this TEDx website. And if you are in the East Coast in the US, we have some workshop which you can run, which you can join, where we will go more into this. If you cannot, then go through this URL. It contains a lot of information about distributed training and inference. And if you have any questions, feel free to ping me on LinkedIn. I'll be more than
Suman,
happy.
also that slide with the layers, if you
Mhm.
can pull that up,
Oh yeah, yeah.
I think that should be a poster to be printed and to be hung on the ceiling of every bedroom.
Oh yeah, absolutely. So I think we can
Not this
spend
one, not this one.
Yeah,
wait,
2 hours only on this, right? So
wait, no, not the KV cache one. The other one, the one with all the different layers
this
and the
one.
different technologies within each layer. It's just the
Oh, I see
mapping.
this one.
The
Okay.
map. Yeah.
Yeah. Yeah, because this is little confusing for me as well. So I thought that to put it here. So yeah, I'll be happy to talk.
Nice.
Next time whenever.
Well, we'll
we have-
we'll ping you to do some more stuff, and then Suman, we also have a few questions we didn't get to.
Yeah.
I think primarily about the efficacy of speculative decoding and
Yeah.
what performance gains you're actually seeing. So stick around if you can jot down your answers in the chat.
Sure.
That would be very, very lovely. I think Amar has some questions and Abhijit has some questions. And I think Ananda Pagnash as well. So nice.
Sure. I'll answer on chat. Yeah, no problem.
Awesome. Suman, thank you very much.
Thank you. Have a good one.
This was absolutely wonderful. And we appreciate having you. Okay.